So this is what our tool looks like. You can see you have two panels here. On the left-hand side, you have a panel where you can read the results, and on the right-hand side, you have the panel for the configuration of your simulations. So let me start with the result panel. Here are expressed the life cycle emissions, expressed in grams of CO2 equivalent per kilometer. And you can read stacked bars, each of the color corresponding to one aspect of the life cycle emissions. The orange bar is related to the emissions during the manufacture of the vehicle. The green bar is related to the emissions coming from producing the electricity. The dark blue bar corresponds to the emissions of producing the fuel. And then we have two bars which correspond to the tailpipe emissions, and we have split that in two parts. This part corresponds to the tailpipe emissions minus the recycled CO2, and the light blue bar corresponds to the recycled CO2. I remind you that the recycled CO2 is neutral from a life cycle perspective. And at the bottom of this bar graph, you can read the different configurations which are simulated. So on the left, you have a battery electric vehicle with a 60 kilowatt-hour battery, followed by a hybrid electric vehicle with a 2 kilowatt-hour battery fueled with E10. E10 is a gasoline which is 90% fossil and 10% renewable. And then you have two plug-in hybrid electric vehicles with a 15 kilowatt-hour battery fueled with E10 as well. And the first one is recharged every day, while the second one is recharged only every 3 days. So this is the result panel, and now we have the configuration panel. In the configuration panels, first you can design your vehicle. So for instance, if you want to change the size of the battery, the capacity, you can select, for instance, a smaller battery, 40 kilowatt-hour, which would be a small urban vehicle. And you can also select a bigger battery, 80 kilowatt-hour, which would be something that looks like a Tesla, for instance. And you have seen, while I was doing that the emissions have changed, they have been updated, and you can see that due to the manufacturer aspect, the bigger battery electric vehicle will emit more CO2 than the smaller one. A big question now is related to the emissions related to the manufacture of the battery. For the moment, it's set by default at 120 kilograms of CO2 per kilowatt-hour. If you are not happy with this value, there is a slider here, and you can move it to either lower values or higher values, and you can see that the results are updated automatically. So why have we selected this default value of 120 kilograms per kilowatt-hour of battery? It's because we have extracted the data from a scientific paper, from the scientific literature. And this scientific paper has reviewed 50 life cycle assessments of battery manufacture. And they found out that the median value among these 50 papers was 120 kilograms of CO2 per kilowatt-hour. So this is the value that we have taken by default. This paper also includes the values for the first quartile of these 50 papers and the third quartile. So if you are not happy with this value, once again, you can change that. And we also refer to another paper from the ICCT, which is not the most recent, actually, even if it's from 2018. But we found this paper interesting as it provides a range of emissions. And so you can see that the range, the lowest emissions they have found is 30 kilograms of CO2 per kilowatt-hour. And the maximum range is well beyond that, even is probably not realistic today. But it was interesting to define what is the range of variation we allow in this slider. So if you want, you can move down to 30 kilograms of CO2 per kilowatt-hour, which is the lowest value we have found in the literature. Next, you can define the usage. And we start with the recharge frequency of your plug-in hybrid electric vehicle. So for the moment, it's recharged either every 1 day or every 3 days. But if you think that it will be even less than that, you can select, for instance, every 7 days. And you can see that the new value has appeared with even higher emissions. And if you hover your mouse over the bar, you can read what is the utility factor of each of these use cases. So if you recharge every day, it would be 77%. If you recharge every 3 days, it would be 48%. And if you recharge every 7 days, it would be 35%. So of course, I encourage you to recharge your plug-in hybrid electric vehicle as often as possible, because you see that the emissions increase when you don't recharge it enough in this use case. So let me focus on the recharge every day for simplification purpose. And then the second parameter is related to your driving profile. By default, we use this yellow curve, which shows the probability density against the daily distance that you drive. And this curve is out of the scientific paper published in 2012 by Plotz et al. This is out of a Germany mobility survey. But we also generated 2 other profiles, a profile for driving shorter distance and a profile for driving longer distance. And you can see here, according to the daily distance, so less than 5 kilometers, between 5 and 25, between 25 and 100 kilometers, and more than 100 kilometers, then when you select a scenario with longer trips, the share of very long trips increases. So it is just a way to recognize what is your driving profile and which one you should select. So let's look at what happens when you change your driving profile. So for instance, if I move from average to short, let's observe what happens for the PHEV. You can see that the emissions decrease, and that's because the utility factor has increased. It is now 88%, because when you drive for shorter distance, you are more electrified. And that's the opposite which happens when you drive longer distance, because you will be less electrified. Now it is only 61%. And you can do the same with climate. So by default, you will use this black curve, showing again the probability density against the temperature. This black curve shows the probability density of driving in France. But if you are not happy with this climate, you can select a colder climate. The blue one is shifted by -10 degrees, and it looks like a Swedish climate. And the red one is shifted by +10 degrees, and it looks like an Australian climate, which is even warmer than the Greek climate, 5 degrees warmer, so warmer than the warmest one in Europe. And same as for the trips, we have simulated one by one for each temperature the emissions related to the vehicles and the energy consumption. It's not just a simulation of the average temperature, it is more complete than this. And so you can see what happens if you change the climate. So if you switch from a temperate climate to a cold climate, you will see the emissions that will increase, because you will take more energy from the battery to heat the cabin and to condition the battery. Last but not least, you have the energy carriers, starting with electricity. And to guide you through the emissions related to electricity, we have extracted data out of a scientific paper written by the Joint Research Center, which is a research center from the European Commission. And they have found out that from a life cycle perspective, the CO2 emissions of producing electricity in 2019 in Europe is 334 grams of CO2 per kilowatt hour. So this is the default value that we have taken here in our simulator. But you can take values from other countries. So for example, Poland would be 805. You can take, for instance, Germany would be 422. And France, with a very low carbon intensity, would be 98. So let's look at what happens when you change the carbon intensity of electricity. So let's move to Poland, which is the worst case. So in this case, it's quite obvious to see that the electric vehicles don't bring any benefits. And here, in fact, the hybrid electric vehicle is the best in class, and even the plug-in hybrid is not interesting in this case. If we move to Germany, that would be this value. You can see that now the hybrid electric vehicle is no longer an interesting option, and the small BEV would be, in this case, the best option. And you can see a competition between the plug-in hybrid vehicle and the big battery electric vehicle. They have quite equivalent emissions. Now moving to average Europe. Still have the same results. The BEV is the best in class. The electric car, the small electric car is the best in class. The hybrid car starts to be the worst one. And you still have a competition between the big battery electric vehicle and the plug-in hybrid electric vehicle, providing that it is recharged every day. And now if we move to France, now the hybrid electric vehicle refueled with the fossil fuel starts to be really bad now compared to the other options. The small battery electric vehicle is still the best one, and you can still see that the big battery electric vehicle and the plug-in hybrid electric vehicle are still more or less equivalent. So this is what happens when you vary the electricity carbon intensity, but now it's also about the fuels. And for the fuels, we have proposed several options, and you can see the details in this information panel. We have fossil-based options, P7, which is the average diesel in Europe, E10, which is gasoline in Europe, and we have also different options for renewable fuels, HVO, which stands for hydrotreated vegetable oil, which is a renewable fuel, and other future fuels, which can be either e-diesel or e-gasoline made from renewable hydrogen and captured CO2. And so let's see what happens if we compare the results we have for the moment with the one we obtained with HVO. And now it completely changes the perspective. You can see that the best in class is now the hybrid car refueled with renewable fuel, thanks to the recycled CO2, which is neutral from a life cycle perspective. And you can see that the plug-in hybrid electric car is also very interesting in this case, now competing with the small battery electric vehicle. And you can see that the big battery electric vehicle is no longer the interesting option in this case, because it emits more emissions than the other options. And of course, the worst case is still using a car fueled with mostly fossil fuels. So this is just an example of some scenarios you can run. Once you have that, once again, you can change any of the parameters and do any variation you want according to your own sensitivity and check what the new result would be. All of this, you will be able to play with this tool, and hopefully you will have fun with it in the website we have designed for you. So the web address is www.carsco2comparator.eu, and when you connect at this address, you will find this simulator. So it's available here just the same way as before. So you can run your own simulations. And you will also find the user guide detailed for this tool, some additional resources where you will have some additional information about how the simulator works, how the experiments were done, and additional information about life cycle.